Now let's talk about the RISC-V Verilog. So here's our Verilog file. Starts out with the name of the file, what it's for, and who wrote it and when and how to get a hold of them. Next, I like to indicate on a complex design how to test whether the design is correct. So saying we can simulate it in model sim by typing in run 200, and if the result is correct, we should see the message simulation succeeded when the value 71 is written to address 84. And I'm showing it in both hexadecimal and decimal because we might be viewing it either way. Next, I define what exactly this module is implementing. So this is our single cycle processor doing the instructions load, store, add, subtract, and or set less than, add immediate, branch if equal, jump and link, just like we worked our way through in the data path in the controller for the single cycle processor. So talk about what's not built. So this doesn't do exceptions, traps, or interrupts, and it uses a little endian memory. Next, I give some more detail about which instructions were implemented. So we've got the 32-bit registers plus including X0, which is hardwired to 0. Here's the different types of instructions that were implemented. For instance, the R-type instructions, and is that add, subtract, and an or, and the fields of those instructions. Do that for each different type of instruction to make it easy when I'm coding up the system to remember what I need to implement. And I also have a handy table of which fields do what for these instructions. Now let's take a look at the test bench. So the test bench should instantiate the device under test. It should apply a clock and a reset, and it should check if the result is correct. So here is the device under test. This is the entire processor, including the data path, controller, and memories. And we're giving it the clock and reset, and we're getting back write data, data address, and memwrite to be able to see what is happening on the memories. These lines were generating a clock with a period of 10 units. And here we're applying a reset for 22 units, or just over 2 clock cycles. So we reset this thing for the first 2 cycles, and then it can run ahead. Now to see if the answer is correct, we said we should write the value 71 to address 84 if it's correct. So each cycle on the negative edge of the clock, we'll take a look at the memwrite signal. If that's true, then a memory write's taking place. And if we're writing the correct value to the correct address, we'll indicate the simulation succeeded. We also had a store to address 80. So if there's a store to 80, we'll ignore that because that wasn't the end of things. But otherwise, if we're writing any different value to any different address, then the program went haywire, something wasn't right, and we'll say that simulation failed. All right, so now let's take a look at the top level module. Top level module was the one from our picture. It had the processor, the instruction memory, and the data memory. And they were hooked up with a program counter instruction going from the processor to the instruction memory, and the data memory getting memwrite, data address, write data, and read data to connect to the processor. The data memory looks just like we talked about in chapter 5. It's a memory with a read port and a write port. So it's got 64 words of memory, each 32 bits wide. To read, this is the syntax to read, and we write synchronously on the rising edge of the clock when the write enable signal is true. Then we write the desired address with the desired data. The instruction memory it also has 64 words, and we initialize it with our program from memfile.dat. So we read these 18 machine language instructions into the first 18 words of the memory. And for the memory to read, this is the idiom for reading the memory. Now let's go into the processor. So the processor consisted of the data path and the controller. And the, this looks like junk sitting here. The data path received the clock and reset, and a bunch of control signals. It produced the 0 output to send to the controller, and it had some 32-bit buses to communicate with the memories. The controller receives the instruction in several different fields. It also receives the 0 signal from the data path, and it produces the control signals for the data path. And remember that we need to declare any signals connecting in between the blocks. In Verilog, you should always declare all of your internal signals. If they are not declared, Verilog assumes they're a single bit. So things like mem to reg, immediate source, or ALU control would misbehave because they had the wrong number of bits. Now we'll continue our process of hierarchy, decompose each block into subblocks. So the controller consists of a main decoder that takes the op field and produces most of the control signals. There is also the ALU decoder that takes ALU op and a few bits of the instruction and produces the 3-bit ALU control signal to the controller, sorry, to the ALU. And finally, the logic to compute PC source, whether to change the program counter. We did that when you have a taken branch. So if branch and the result is 0, or if we're doing a jump, then we want to change the program counter. All right, so let's take a look at the main decoder. The main decoder, as we described in the controller section, takes a 7-bit op field, and it produces a bunch of control signals. So we described it as a truth table. In the system Verilog, the typical idiom for a truth table is a case statement. So we have cases for the different op fields corresponding to different instructions. We could, for each case, have a begin and an end and a whole bunch of assignments to give the different control signals their value. And that's kind of tedious to type it over and over. So instead, let's define a 11-bit bus called controls that will have all of the control signals. So we'll give controls a value in the case statement, and then we'll break it apart into the different controller outputs. So for example, if op is 0110011, that's an R-type instruction opcode, and the control signals would be 1 for reg write. It would be XX for immediate source, because for R-type instructions, the immediate's not used, so don't care. ALU source is 0, because we're choosing the source B from the register file rather than the immediate. Branch is 0 because an R-type instruction is not a branch. Mem write is 0 because R-type instructions don't write to the memory. Mem to reg is 0 because this is also the result source signal because we are taking the result from the ALU. Jump is 0 because it's not a jump instruction, and ALU op is 10 because we need to look at the function field of the instruction to say what kind of ALU instruction. So the other control signals are similar. There's a default case that puts out X's for everything. So if we get a bad instruction in, we should get a bunch of X's into our simulation. So that's the main decoder. ALU decoder is a similar style. It's also described as a truth table. And so we can look at ALU op and the bits of the instruction, and based on that, produce the ALU control signal for each possible ALU op and instruction. Now we have the data path. So the data path receives clock and reset externally. It receives a number of control signals from the controller. It returns the 0 flag to the controller, and it puts out some 32-bit buses to talk to the memories. Here's some internal signals. We have program counter, immediate, source A, source B, and result, and so on. So here's different pieces. For the next program counter, we have the flip-flop with the program counter. We have the adder to do PC plus 4, another adder for branch, and the multiplexer to choose whether next PC was PC plus 4 or PC plus the branch offset. And PC source was the control signal to do that. Then we have the register file that takes clock. It takes the 3 different register addresses, RS for source 1, source 2, and destination. It takes the value to write when we're writing a result, and it reads out the 2 sources on the buses called source A and write data. We also have an immediate extender that takes the bits of the instruction and the IMM source control signal and puts out the appropriate immediate. Finally, we have the stuff around the ALU. So we have the source BMUX that chooses the input from either the second source of the register file or from the immediate sign extender based on ALU source. That's source B. Now the ALU operates on source A and source B. The operation is described by ALU control. The result, it goes on to ALU result. And we also put out the control signal 0, the flag, to indicate whether the result was 0. And finally, we have the result multiplexing. Here's the immediate extension logic. So there are 4 possibilities of IMM source for I-type, S-type, B-type, and U-type instructions. And we create the extended immediate by appropriately swizzling the immediate bits out of the instruction. Here's our register file. This is a standard 3-ported register file like we described in chapter 5. It's got 32 entries of 32 bits each. It's synchronous, so it takes a clock and a write enable. Ports 1 and 2 are the read ports. So we take an address on port 1 and an address for port 2. And we read out data for port 1 and data for port 2. Port 3 is the write port. So it also takes an address, takes the data to write, and it takes a write enable to say whether to write. So to do the write, we write synchronously on the rising edge of the clock. If the write enable for port 3 is true, then we write to the address register specified by WA3, data specified by WD3. To do the reads, we check if the read address is 0. That's register 0. Register 0 should be hardwired to 0. So if it's not register 0, then we return the value from that address of the register file. Otherwise, we just return 0. Finally, there's other miscellaneous blocks. So this was the idiom for an adder, y equals a plus b. Here's the idiom for a resettable flip-flop, always at pause edge clock or pause edge reset if reset q is 0, otherwise q gets d. Here's the idiom for a 2-input mux, assign y equals s question d1 colon d0, and so forth. And so that concludes our Verilog for the single cycle processor. And you see how the diagram of the processor directly corresponds to the hardware. And our approach was to look at each piece of hardware and write the corresponding idiom in the Verilog.